Excuse me. What's up, guys? This is Tuesday night. Just doing my physics homework. Um, 2006 E&M. You can see it's number one right there. And I think we did this problem as a test question already. So we've probably seen this before, but let's go through it. Square side A contains positive charge Q, lower left, and negative Q's everywhere else. Point P is located in the center. On the diagram, indicate with an arrow the direction of the net electric field at point P. So if we look at all the individual fields at P, right, we have a negative charge here, so that's going to create field this way. We have a negative charge here, that creates field this way. We have positive charge here, that creates field this way, and a negative charge here, which also creates field that way. So if we take all of that, right, this one and this one are going to cancel. Those two from the negative Q in the top left, right, and then positive Q in the bottom left are going to combine, and we'll get, if I can erase right here, the total field towards the top left. Put a little E on that, electric field. On the diagram, so indicate with an arrow direction of the net electric field at point P. There we go. Excuse me. Derive the magnitude of the electric field at point P. So what is the size of the field? Well, we said already that the bottom right Q and the top left Q are going to cancel. So we don't even have to really worry about them. We just need to worry about these two Qs and what the value of their electric field is going to be. So we could do them one at a time and add them together, right? Whatever we want to do, but we have to derive an expression for each of the following. Now, the hardest part right here is determining the distance. Actually, let me do it. What is this distance right here? Right, we know the baseline is A, right? But what's the distance here along this side right here? So I think the easiest way to do this, right, because the first thing we have to do is figure out that distance, right? What is, I don't know, we'll call it D. What is D? So I'm going to split this into a little right triangle here with sides A over 2. And then since this is a right triangle, we can use either Pythagorean theorem or trigonometry to figure out what D is going to be, whichever way is easiest. So maybe we use Pythagorean theorem, right? So D is going to equal the square root of A over 2 squared plus A over 2 squared. That will give us square root of A squared over 4 plus A squared over 4. And that'll give us 2A squareds over 4, which would be A over 2, or A squared over 2, right? The square root of A squared over 2, which would be A over root 2, or root 2A over 2, right? If we get the ration, because nobody likes to have square root functions in the bottom there. So there's our value for the distance between those two. I did that right? I'll have to double check that later. We probably could have used special triangle rules and just, this is 45, 45, 90, and just said this is root 2 times x, which is A over 2. So we could have used a shortcut there. I mean, but what's the fun in that? So there's our distance A. So now we just have to use Coulomb's law equation twice and figure out what our value is for, I'm going to zoom in a little bit here, the electric field. So the electric field is going to be K Q1 Q2 over R squared. Oh, that's electric force. I lied. Just KQ over r squared. Electric field is KQ. I guess we don't need the 1 either. KQ over r squared. So we have that one. It's actually the sum of the KQs over r squareds. So we can pull out the K, we can pull out the r squared because those are both constants, right? Because I guess it would have been smarter to call this r. This is going to be a distance r. This is also a distance r, the same distance r. So r is a constant. We can pull that out. K is a constant. We can pull that out. And we'll get electric field is equal to K over r squared times the sum of the Q values, right? Which the two Q values are just Q and Q. So 2Q. So E is going to equal K over r squared times 2Q. We kind of take the absolute value there, right? Because we know which direction those fields are going in. This is almost an absolute value, right? It doesn't really matter what that is, because the electric field direction isn't dependent on necessarily what value that Q has. And then we can go ahead and solve here, right? The only thing we have to plug in is the r squared, which we know is root 2a over 2. So we'll have, if I come up here, K over 2a squared over 4, right? Because that's r squared. So squared is 2, squared is a squared, squared is 4. That factors down to 1/2 times 2Q. 2 comes to the top, I think. So we'll get K times 4 times Q over a squared. And it says we should have this in given quantities and fundamental constants. Now, unfortunately, K is not a fundamental constant, but K is equal to 1 over 4 pi epsilon naught. And 1 over 4 pi epsilon naught is constants, so we could replace it there. The 4 would cancel with the 4 here, and we would get Q over pi epsilon naught a squared as the value for the electric field. And we're talking about magnitude, so we don't even need to put a direction on that. We just get Q over pi epsilon naught a squared. Let me double check that, see if I got that right before I just move on and assume that I'm right. Because, you know, as much as I like to say that I'm always right, I'm not always right. Q over pi epsilon naught a squared is correct. So that works. All right, cool. So next is the electric potential. So let's look at the electric potential. Potential is a little bit nicer because it's a scalar. So we just have to add up all the potentials from all of those values. So potential is K, the sum of the K Q's over R, right? Potential just gets that, changes that R squared to an R. K is constant, R is constant, just the sum of the Q's then. So potential is going to be K over R. We can replace with the root 2a over 2 times the sum of the Q values. This one, the positive and negative Q's do matter. So we have 3 negative Q's and a positive Q. So we'll get here 2k over root 2a times positive Q minus Q minus Q minus Q cancels. We get negative 2Q. So our potential is going to be negative 4k over root 2 a times q, right? The -2 multiplies out with this 2 in the front. Again, k I don't think counts as a fundamental constant, so we should replace it with the 1 over 4 pi epsilon naught, which means the 4s are going to cancel again, and we'll get potential is equal to q over, sorry, negative q over root 2 times 4 times pi times epsilon naught times a. Can we do anything with the 4? I don't think we can do anything with the 4. We probably can to get rid of that root 2. Four, this I'm doing something stupid right now that you definitely don't have to do, and there's probably an easier way to do this, but 4 is root 2 times root 2 times root 2 times root 2, right? So if I put another root 2 in there, I would get root 2 to the 5th power. Is it nicer to write that as root 2 to the 5th power? I don't know. I'm going to leave it like that. Potential is negative q over root 2 times 4 times pi epsilon naught over a. Let me check the answer really quick. They have their 4 canceled. Did I say the 4 canceled and then not cancel the 4? I said the 4 canceled and then didn't cancel the 4. I said it right here. I said the 4 is going to cancel with the 4 when we substitute in the k, and then I just didn't do it. Why am I trying to get rid of 4 when it's not even supposed to be there? You guys are probably watching this, Mr. Knight. 4 doesn't even belong there. All right, so there we go. The 4 canceled when you substitute in the k. So we put a nice little multiplication in there to let people know that we put that times there. That's not a space, that I made a mistake. I just left a lot of space for that multiplication sign. So there is our potential, negative q over root 2 times pi epsilon naught a. A positive charge is placed at point P, then moved from P to R, which is at the midpoint of the bottom side of the square. As the charge is moved, is the work done on it by the electric field positive, negative, or 0? Oops, so let's see here. We take a positive charge. Let me erase some of this stuff so we can see here. So we take a positive charge and we move it to R. So there's a couple ways to look at this. One is that generally speaking, right, these electric fields are going to be canceling out, right? So in general, the electric field points in an upward to the right direction, right? I mean, it changes a little bit because these vary in strengths, and maybe it kind of branches off kind of down this way as you get closer to the minus q, and maybe it branches a little bit up this way as you get closer to the minus q up here. But for the most part, right, our electric field is in like this kind of direction, right? So because it has a component that's always going to be up to the right, right? The component of our electric field, we're always going to have a component of the electric field that goes up to the right. We're kind of moving this not perfectly against the field, right? Perfectly would be moving it down to the left, but we're moving it against the field, right? The field goes to the right-ish and up-ish. Our positive particle is moving straight down. So because we're moving it against the field lines, when protons would usually move with field lines, right? It doesn't say it's a proton, but positive particles move with the field line. Our electric field's doing negative work. We're doing negative work here. So let me explain my reasoning. Yes, exactly what I wanted to happen. Thank you for doing that. How do I get this to do this without making me look stupid? There we go. All right, that's what I wanted. Okay, so did the X go up here? The X did go up there. It's going to be negative because the positive particle is moving against the S goes before the T. The electric field lines, or against the direction of the electric field. All right, so because the positive particle is moving against the direction of the electric field does negative work. Excuse me. All right, so there's our answer for C. You can also explain it using potential difference, right? The potential difference between point P and point R, you're going to get a more positive potential at point R than at point P, right? Because we're moving it closer to this positive charge. So it's going to be more positive. And if you're moving a positive particle to a more positive potential, we have to do negative work. The field would want to move a particle from high potential to low potential. And if we're going from high potential to higher potential, we're doing the opposite of what should be happening. So that's negative work. All right, describe one way to replace a single charge that would make the electric field at the center of the square equal to 0. All right, we want the electric field at the center to be 0. There's two ways to do that. We can either make this top Q a positive Q, right? That way it would create field downward, which would cancel with the positive Q here. Cancels, 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 cancels. Electric field is 0. The other way to do it would to make this Q a negative Q, because then cancel, 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 everything cancels, and we get 0 electric field. So you can the top right minus Q with a plus Q, so its field cancels with the bottom left. Or you can replace the bottom left Q, bottom left plus Q with a minus Q, so it cancels with the top right. Either way works. Both of those are acceptable. And describe one way to replace a single charge in this configuration such that the electric potential is 0, but the electric field is not 0. So we've seen the two ways to change it to make the electric field 0, right? You can either make this a positive Q and this a negative, or this a negative Q. And if we kind of take a look at them one at a time, right? Just to see, right? Well, I guess this doesn't work. If we replace this positive Q here, or this negative Q with this positive Q, that would make the potential in the middle 0, right? Because you would have positive Q canceling with negative Q, positive Q canceling with negative Q. They would cancel because we had 2 positives and 2 negatives, but the electric field would be 0. So this doesn't work for potential. And this one would never work for potential and still doesn't work for electric field. So that doesn't work either. So we need the positives and negatives to balance in terms of the number that we have, but not balance in terms of where they're located on so that the electric field doesn't balance. So we could either replace this one with a positive Q, right? That would give us 2 positive Qs and 2 negative Qs. Potential will cancel. And if we look at the direction of the field lines, right, this Q would create field this way. This Q would create field that way. This Q would create field this way and this way, right? So those definitely, there's no field going down. So that would definitely not cancel. So we would have electric field. Or you can replace this Q with a positive Q. That way, let me just do it in black so we can see. Right, if we replace this with a positive Q, this stays a negative Q. We still have positive Q, negative Q, negative Q. So 2 and 2, those cancel in terms of potential. But when we look at electric field, right, this Q creates field this way, this Q creates field this way, this Q creates field this way, and this Q creates field this way. And we have everything on the right side, nothing going left side. So this definitely not going to cancel out either. Right? We get a total field that points straight to the right. So we have electric field there. So again, 2 options for answers there. We could either make the bottom right positive or negative Q positive, or the top right negative Q positive Q. So let me just answer with one. Make the bottom right minus Q a plus Q. So 2 positive Qs and 2 negative Qs will make the potential 0. But the electric fields in the middle do not cancel. And I mean, you could draw a picture or something, right? I had plus Q, minus Q, minus Q, right? And I said field this way, field this way, field this way, field this way. Those are definitely not going to cancel, right? Won't give us an electric field. The total electric field will be straight up. So verify that that is the case. And that is it for problem number 1. Great work, me.